Recording has started.
Okay. Hello everyone. So today I along with my teammates Abhishek and Atif are going to present our views on dense convolutional network. So I will take up the introduction part and then Abhishek will tell us about the architecture and then Atif will share his views on result section. So, in this paper, dense convolution network, which are also known as DenseNet, has been introduced, which connects each layer to every other layer in a feed-forward fashion, which embrace the observation that convolutional networks can be substantially deeper, more accurate, and efficient to train if they contain shorter connections between layers close to the input and those which are closer to the output. Next slide, please, Abhishek. Okay, so here now I'm going to tell you about some different CNN architectures and their improvements, because the exploration of network architectures, has been a part of neural network research since their initial discovery. So the increasing number of layers in modern networks amplifies the difference between different architectures, and they motivates the exploration of different connectivity patterns and the revisiting of old research idea. So first I will go with LINET. So LINET is one of the earliest neural networks that employ the convolutional operation, combining newly developed back propagation algorithm with convolutional neural networks. And then AlexNet came into picture, and it has many showed many improvements. So the first one was ReLU. So using ReLU nonlinearity, deep CNNs could be trained much faster than using the saturating activation function like sigmoid. So the authors of AlexNet also reduced overfitting as improvement using some different couple of different methods. And then there was one improvement on data augmentation by random crops. So what the authors did, the authors of AlexNet basically extracted random crops of size 227 by 227 from inside the 256 by 256 image boundary to use as the network's input, and they increase the size of the data by a factor of 2048 using this method. After that, there is one more model which is VGGNet. So what is this? This is basically a stack of 3 into 3 convolution kernels is relative to the field of view of a 5 into 5 convolution kernel, and in this way there can be fewer parameters. So the non-linear transformation increases the ability of CNN to learn features. And second one is that a 1 into 1 convolutional kernel is introduced, which increase the non-linearity of the model without affecting the receptive field. Winding machine is equivalent to linear transformation. And then in 2014, inception net improvement model came with some improvement. So what the main idea of that is to design an inception model and increase the depth and width of the network by continuously copying this inception modules. But Google Net, what does it did? It mainly extends inception modules in depth, and its design philosophy is to change the full connection to a sparse architecture and try to change it to a sparse architecture inside the convolution. So these are the basically the improvements in some of these different architectures. Abhishek, can you?
Yeah.
So in this slide also these improvements are mentioned, which I told explained in the earlier slide. So these are only the improvements. Now I'm going to tell you the problems which were caused by increasing the depth. So, what was the first problem? The first problem was the problem of gradient explosion or dissipation. So, why does this happen? This happened because as the number of layer increases, the gradient of back propagation in the network will become unstable with continuous multiplication and become particularly large or small. So among them, the problem of gradient dissipation often occurs. So to overcome this problem, many solutions have been devised, such as using batch norm, replacing the activation function with ReLU, and etc. And the other problem was of network degradation. So what happens? as the depth increases, the performance of network was becoming worse and worse. So which is directly reflecting in the decrease in the accuracy on the training set. So the residual network solves this problem. Next slide. Yeah. So now let me tell you about the advantage of the ResNet. So the first and foremost advantage was the is that the gradient can flow directly through the identity function from later layers to the earlier layer. However, the identity function and the output are combined by summation, which may impede the information flow in the network. Next slide. And to further improve the information flow between layers, we propose a different connectivity pattern. We introduce direct connections from any layer to all subsequent layers. As you can see in the figure, the channel-wise concatenation. So they are basically creating the shorter paths. And the important difference between the DenseNet and the existing network architecture is that the DenseNet can have very narrow layers. Yeah, next slide. Now it's showing the growth rate. So the growth rate regulates how much new information each layer contributes to the global states. And with DenseNet, it becomes accurate and efficient because there are shorter connections, as we can see, between input layers and the output layers. Next slide. Now this here we are showing the basic difference between ResNet and DenseNet. So traditional convolution feed forward network connects the output of the Lth layer as the input to the L plus 1th layer, which you can see in the first one, and it gives rise to the following layer transition, which is XL is equal to HL XL minus 1. So here ResNets add a skip connection that bypasses the nonlinear transformation with an identity function, which is given here as XL is equal to HL XL minus 1 plus XL minus 1. So consequently, the Lth layers receives the feature maps of all the preceding layers, which are x0 to xl minus 1 as input, and where this x0 to xl minus 1 refers to the concatenation of the feature maps which are produced in the layers 0 to L minus 1. Now, because of its dense connectivity, we refer to this network architecture as dense convolution network. And for the ease of implementation, we are concatenating the multiple inputs of the identity function. So now Abhishek will tell us about the architecture. So
Okay. Thanks, Sarah, for the introduction and for the preceding part. So let's go going through with the architecture. I'm assuming everybody can hear me. So here, what we have is this is the let's go step by step here. What we see here is the input. So the input which has a lot n number of, let's say, the feature maps that will be there. Then in the blue outline is something called as a dense block, and then we have the transition layer. So when we are talking of a dense net, there are four things which primarily are very important. One is the growth rate. As Hera mentioned, this is about the amount of information that you want to transfer from each layer to the subsequent layers for the overall for the overall information to be transmitted. The second is with respect to the dense blocks, that is the blue outlined layer. A dense block might have several convolution layers that might be stacked, and then we have the transition layers, which are typically we will see in the next succeeding slides, and the composite layers. So as we see in this example here, initially we have fewer feature maps, then we are adding each of the feature maps to the earlier layers, and that increases, and that's how, and then there is concatenation, etc., that happens. This is the broad overall idea. Let's go a little bit deep into this. So as we see from the let's see from the left side, we have an input feature maps that would there is some sort of convolution that has happened, after which there are dense blocks. Here we can see as an example, we have three dense blocks that have been here. In between the dense blocks, we have something called as the transition blocks that we mentioned the transition layer that we mentioned previously. In the transition layers, we are typically talking of about doing there's sort of the convolution and the pooling operations. So essentially it's a compression that we are doing, because pooling will reduce the feature map sizes. And then for post all the dense block, we have the pooling, which is nothing but the global average pooling that has been used by the authors here, followed by the linear, and then we'll get the final output of one of the classification, one of the 1,000 classification of the classes. So if you look at the composite layer next, we have it is nothing but a sequential, we have a batch norm which has been followed by the ReLU, and then we have a 3 cross 3 convolutions that are there. What is important here is in this we see that the k, as it was earlier mentioned, this is the growth rate. So what we need what we are saying here is this is a factor, this is kind of an hyper parameter which has been defined by the authors in order to make sure that the numbers do not increase. So what do I mean by this is, let's take the next example. Let's take this example. This is nothing but a DenseNet 121 architecture for the ImageNet challenge that was there. Now assume we initially told that each of the layers is connected to each of the preceding layers before this. Now in this block, if you see, there are 4 dense blocks. So we are saying block number 4 is not only connected to 3, it is also connected to 2, also connected to 1. So now assume instead of 4 blocks, you had 10 blocks. So essentially, the block number 10 would be connected to all the previous 9 inputs. So this will increase the number of this will increase the number of parameters for us. That will be the problem, because this is one of the things, the advantages of DenseNet is that we are getting a good enough accuracy with a very less number of parameters compared to the ResNet. Okay. Now let's take the input. The input typically to an ImageNet has always been a 224 cross 224 cross 3, which we have the RGB image, sorry, which was followed by a convolution. Here, the authors have used a 7 cross 7 convolution with a stride of 2, and we get the output as 112 cross 112 cross 64. Now, why is this 64? Because we say in this architecture, the value of k was taken as 32, which is nothing but the growth rate. 32 into 2, we got this 64, which was followed by batch norm and ReLU, and then we are doing a max pooling. Max pooling will reduce the feature map sizes, and hence this 112 will shrink to 56 cross 56 cross 64. Post that, what we have is, let's take one layer as an example. In this layer, we have the batch norm and the ReLU, followed by a 1 cross 1 convolutions also we have, which will give 4k feature maps. So when you have 4k, k value was 32, 32 into 4 is 128, and hence we get 56 cross 56 cross 128 feature maps, which are again followed by a batch norm and a ReLU. And then at the end, we also again typically have a this 1 cross 1, or it can be a 3 cross 3 also. Sorry, it should be a 3 cross 3, guys. Here it was just a mistake. So this will typically become 56 cross 56 cross 32. Now this 56 cross 56 cross 64 was concatenated with this 32, and hence we finally get 56 cross 56 cross 96. So this is the one of the layers of the dense block we are showing this. Now if you look at the typical transition block, we said the transition blocks we are taking in order to, it's kind of compression that we are doing. So for a compression kind of thing, starting with a batch norm and a ReLU, we did a 1 cross 2 convolution. 1 cross 2 convolution will help to reduce the feature map sizes and also preserve the non-linearity that would be there. So this would become 28 cross 28 cross 128, followed by a global followed by an average pooling. That is what the authors have proceeded, and then still be, and with a stride of 2, and hence we still get it as 28 cross 28 cross 28 cross 28 cross 128. Now at the end of this, ultimately there are what we can see from this diagram is there are 4 dense blocks. There are 3 transition blocks that are in between, and after which there is this average pooling and the fully connected block. So the input after all these operations, what we get is 7 cross 7 cross 1024, which is the input to the average pooling, which when you put a 7 cross 7 kernel on top of 7 cross 7 cross 1024 feature maps, you will obviously get a 1024. This will be there, and on for this, when you do it to the fully connected layers, you will have a thousand outputs, which are nothing but for the ImageNet classes. Let me just go to the next one. This is nothing but the architecture for DenseNet. Now DenseNet, as we mentioned, there might be various designs or iterations of DenseNet 121, 169, 201, as we see here. And the growth factor, they have constantly maintained it as 32, or in some cases like a 161 as 48. What we will do is just try to demystify this in the diagram, and then try to understand what does this 121 come up to. So it's the same thing which you have taken from the previous. So earlier, initially the image, we did a convolution on a 224 cross 224. It was 7, we can see here that it was 7 cross 7 convolution with a stride of 2, and hence we get 112 cross 112, followed by max pool, which has reduced the feature maps by 256 to half on both the height and the width. And essentially, as we said earlier, there were 4 dense blocks. three transition blocks. Now for each of the dense blocks, we have 1 cross 1 convolution followed by a 3 cross 3. For the dense block 1, this was in 6 times done. For the second time, it was 12, 24, and 16. So as we see, typically it's as we grow deeper into the network, the size of the number of layers gradually increases. This dense block was also taken into 16. So that is how the authors have proposed this architecture. Now for this 121, what we see here is it is 1 cross 1 we have 6, and 3 cross 3 also we have 6. So this is essentially nothing but 12 totally for the dense block. So let's consider this 6 plus 6, 6 plus 12 is 18, 18 plus 24 is 42, 42 plus 16 is 58, and into 2, because essentially each of them is 2 times, sorry, 6 times or 12 times. So 58 into 2 is 116, followed by which we have three transition layers, and hence we get 116 plus 3 is nothing but 119. Earlier there was a convolution, and hence this will become 120, followed by we also did a global average pooling that was there, and hence we are getting 121, followed by the fully connected layer that we are talking about. So this is kind of one example that we have taken for the image densenet 121 that we see here. Let me go to the next one quite quickly with respect to the advantages that was there. So as Hira had mentioned, it was about the strong gradient flow that is there. Even in resonets, yes, there is a kind of a gradient flow that has happened. But what is important to see here is each of the dense blocks, since we mentioned since we have the growth rate that has been defined implicitly here, one is the less number of parameters that we'll encounter. The other thing, it gives the advantages of ResNet also, that there is the flow of the gradient through the network will happen, and the feature maps in all the layers have direct access to the loss function and the gradient. What I mean by this is, since this feature maps are also connected to this to the preceding one, and also to the initial things that are there, so following by the chain rule that we studied, there would be no vanishing gradient problem. The second thing what we mentioned was with respect to the parameter and the computational efficiency. In a ResNet, it is typically C cross C, that is the big O times. Here it will be L cross K cross K. What is L cross K cross K? Let me say this K is nothing but the growth rate that was defined earlier. L was the initial number of feature maps that we had, and hence here in the first case we'll have correlated features. Here we'll have diversified features. In what will typically happen is when we go through the convolution network, the first stage, as we studied earlier in the lectures from Professor Mayank, was that initially there would be the initial layers would be able to capture much bigger things. Then when we go on to the preceding layers, from textures, part of objects, etc., these are the kind of things that would get captured from the image. That is what we are mentioning here. The third and the last I'll just quickly go through is about the low complexity of features. Why do we say that? Is because if you let me just take it a little bit here. So initially we had x, then let's take it as a function of h1 of x, h2 of x. Everything has been connected here with respect to this, and this is ultimately what we are giving it to the classifier, and the features are also getting in an increasingly complex type. So here we will have simple features, and going for further deep into the network we might have complex things. Now let me just go to the next one. This is the example that I was talking about, that when we see in a typical CNN, this was one of the examples that professor had mentioned in the class. We are assuming this is the car. Initially we get the low level, mid level features, and then the high level features. We are finally giving it to the trainable classifier that is there. Now why we said that it maintains low complexity of features, if you look at this, essentially y is nothing but we are concatenating everything from w0 of x to w1 h1 of x, everything connected together to the w4 h4 of x, and hence the features become increasingly complex, and we are using the features at all the complexity levels. And hence we are saying that this network, this dense net, compared to resnet, even though it is able to take much of the complexity features with a relatively less number of parameters, and that is because of the growth rate. Now with respect to the results and other things, our friend and colleague Atif will take through. Thank you guys.
Hello everyone. So this is Atif. I'll be explaining the result and analysis part. So here in result part, what we did is we have taken the various data sets like Cipher 10, Cipher 100, and the ImageNet, and we have just tried to do the analysis on various ResNet and DenseNet things, which are of 110 layer ResNet, ResNet 1001 layer, DenseNet 100 layer, and DenseNet 250 layer. We have just tried to represent the data on the like mentioned bar graphs with the data augmentation thing and without the data augmentation thing. Data augmentation is just a strategy that enables the practitioners to increase the diversity of data available for the training models without actually collecting the new data. Data augmentation techniques are commonly used to train the large networks, And here the Cipher 10 is like the data set. It consists of 60,000 32 by 32 color images in 10 classes with 6,000 images per class. On the other hand, the Cipher 100 is also the type of Cipher 10 datasets, and here there are 500 training images and 100 test images per class. So on the very first slide where we have like the Cipher 10 results, on this result we have just trying to show the like stats of representing the test error with data augmentation and without data augmentation statistics. Here we can easily see that the test error is coming relatively lower when the data augmentation thing is done, and where when we are using the like the without data augmentation thing, the test error is coming relatively higher. For example, on ResNet of 110 layer, we can see that the test error is 6.41 with data augmentation. On the other hand, ResNet 110 layer, the test error like it goes till 11.26 without data augmentation thing. On the other hand, if we see the lowest thing, that is DenseNet of 250 layers, so the test error comes over around like 2.6 percent when we use the data augmentation thing. On the other hand, if we are not using data augmentation thing, the test error comes on 5.2 percent. Abhishek, can we have a next slide, please?
Sure.
Okay, so on the next slide, the same thing is done on the Cipher 100 dataset, which I have told earlier. So here we can also see that the ResNet 110 layer gives us the 27.22% test error if we do the data augmentation thing. On the other hand, if we are not practicing data augmentation, the same test error goes around 35.58%, which relatively gives us the the quite good number of difference in test error. On the other hand, if we see the lowest part, that is DenseNet 250 layers, 17.6% is the error with data augmentation thing, and 19.6% is the error if we are doing without data augmentation thing. The difference over here is 2, but relatively there is some difference, right? So the data augmentation thing should be there. Abhishek, can we have
Mm.
next slide, please? Okay, so the next slide, the results have been shown on ImageNet thing. So the ImageNet is an image database organized accordingly with the WordNet hierarchy, in which each node of the hierarchy is depicted by hundreds and thousands of images. Here we are just trying to show the top one error percentage respective to parameters that is capital M and G flops. G flops are nothing but a unit of measurement used to measure the performance of a computer's floating unit. Here we can easily see that if we use the DenseNet thing in place of ResNet, then the percentage error is coming relatively lower. For example, on the very first figure, that is parameter M, the DenseNet 264, where case values is 48, we can see the error is lowest. On the other hand, the same thing if we are observing on G-flop thing, where the dense net is 264 and k value is 48, the comparatively top one error percent is also found the lower end, that is 20.27, which I believe. So this shows the better performance of DenseNet, and we can say that the efficiency also improved with the lower error percentage. Abhishek, can we have next slide, please? So the next slide, we are just gonna discussing the further improvements, and on this, we just propose the MST net fundamental idea. So on this, we have that like multiple classifier with varying resources demands are trained such that the test time can be adaptively, I mean, it can be load, or we can say that varied. On the other hand, the resources can be limited device, and image can early exit from the network for a relatively coarser image classification. Image classification, when we propose, then it is nothing but defined as the task of classifying an image from a fixed set of categories. Many other computer vision challenges, such as object detection, segmentation, can be reduced to image classification. Here we propose the anytime classification and budgeted base batch classification, which are nothing but the two settings for image classification with like computational constants. Anytime classifications example can be of mobile applications on Android devices, Here it can be like the network thing, which is like generally forced on the output of a prediction. And on the other hand, the budgeted based classifications example can be search engine like iOS based Safari or like normally Chrome engine. This can be represented like one to many thing if you say in the networking terminology. And on the other hand, it can be termed as a fixed computational budget which is shared across a multi-domain or like large set of network. On the other hand, we also propose the thumb rule, which like basically says that companies can improve the average accuracy by reducing the amount of computation spent on easy cases to save up the computation for hard cases. Uh,
Yeah.
can we have next slide? So the on the next slide, the multi-skill dense net architecture is represented and as we say that the thumb rule is being implemented over here. We just observe the image based on the cat value and threshold techniques. Here the classifier 1, 2 and 3 represent various images with cat equals to zero point 0.2, zero point 0.4 and zero point 0.6. On the other hand, they have threshold values which can be like greater than zero point 0.2, greater than and less than zero point 0.4 and less than zero point 0.6. We have also observed that in this thing, the upper parts are for the image without downsizing, and the lower parts, like the lower thing, is based on the image with the smaller scales. Can you have next slide,
Mm.
please? So this current slide is technically based related to the previous one. So here we can see the easily that the test input when we are putting here. So the easy example that is the cat only is getting into the category of classifier one. On the other hand, if we put a cat and a background and on the head of cat, we can see that there is a cutted part of like watermelon base. So that can be a hard example and it is technically categorized in the hard in classifier 4. We also observed that the inference speed is 2.6 faster than the ResNet and 1.3 faster than the DenseNet if we are doing such thing. So this can be done to improve the like performance or efficiency, which I believe. So my part is over and that's it. Thank you so much.
Okay, I'll stop the recording. Okay. Thanks, Professor. Thanks, everybody. I'm